All right, let's unpack this. We're diving deep into gas phase MOFs today, breaking down episode 85 of Cocktail Party Chemistry.
Definitely some cool stuff in there.
Yeah, I was reading through the source material, and
Yeah.
I was pretty blown away by
Mm.
how much potential
Yeah.
this technology seems to have.
It's amazing.
But before we get ahead of ourselves, maybe we should start with the basics.
Sure.
What exactly is a MOF?
So MOF stands for Metal Organic Framework. And it's basically a really, really porous material. Like, imagine a sponge,
Yeah.
but with holes so tiny you can't even see them.
So like a microscopic sieve?
Exactly. A sieve at the molecular level.
Okay, so we got these tiny sieves. What makes them so special for dealing with gases?
Well, you can actually design them to be picky eaters, so to speak.
Picky eaters.
Yeah, like they can selectively trap certain gases,
Oh, interesting.
like carbon dioxide, hydrogen, methane.
Mm.
It all depends on the size of their pores.
So you're saying they can differentiate between different gas molecules?
Yeah. Exactly. We can essentially tune the pore size of the MOFs
Wow.
so they only capture the gases we want.
Hold on. We can actually control the size of those microscopic holes.
Yep. It all comes down to the chemistry. By tweaking the metal ions and the organic linkers that make up the MOFs, scientists can engineer the size and shape of those pores.
That's incredible. It's like we're building custom-made containers for gases.
Yeah.
But why is this such a big deal?
Well, think about all the challenges we're facing. Climate change, clean energy. MOFs have the potential to play a major role in tackling these issues.
Okay, I see where you're going with this. Give me an example.
Sure. Take carbon capture, for instance. We need to find ways to reduce CO2 emissions from power plants, right?
Right.
MOFs could capture that CO2 directly at the source.
Really?
Yeah, and store it safely.
So these tiny sponges could actually help fight climate change.
They have the potential to. And it's not just about CO2. They can also store hydrogen, which is a clean energy source.
That's fascinating. So we're using chemistry to design materials that could change how we approach energy and the environment.
Precisely. It's a perfect example of how fundamental science can lead to real-world solutions.
Speaking of other approaches, this episode of Cocktail Party Chemistry also mentions nanoporous materials.
Right?
I remember them talking about that in a previous episode as well.
Yeah, they have tiny pores that can capture gases, too.
So are they like competitors to MOFs in the world of carbon capture?
I wouldn't say competitors. Think of it more like different tools for different jobs.
Okay.
Both nanoporous materials and MOFs have their own strengths and weaknesses.
So it's about finding the right tool for the specific application.
Exactly.
Well, it sounds like we need all the tools we can get in the fight against climate change.
Absolutely.
This is reminding me of something else Cocktail Party Chemistry mentioned about MOFs. I think it was in episode 16 they were talking about MOFs in drug delivery.
Oh, yeah, that's a really interesting area of research.
So these tiny sieves aren't just for gases.
Nope, not at all. The same principles that let them capture gases can be applied to other molecules. Researchers are looking into using MOFs to deliver drugs to specific cells in the body.
Oh, wow. So like targeted drug delivery.
Exactly. Imagine delivering medication directly to cancer cells, for example, minimizing side effects and increasing effectiveness.
That's amazing. It seems like MOFs have a lot more potential than we might initially think.
They really do, and we're only just starting to scratch the surface of what's possible.
It's kind of blowing my mind to think about how these tiny things could have such a huge impact.
Yeah, it's pretty incredible.
So we've talked about their potential in capturing CO2, storing hydrogen, even delivering drugs. This episode also mentions another application. Let me see if I can remember. Oh, right. Water purification.
Yes. MOF can be designed to trap and remove pollutants from water.
So we could use them to clean up contaminated water sources.
Potentially, yes. It's a promising area of research.
It seems like every time we look at MOFs, we find another potential application.
They're incredibly versatile.
Definitely living up to their game changer status.
For sure.
This deep dive into one episode of Cocktail Party Chemistry has opened up a whole world of possibilities. But before we get too far ahead, I'm curious to learn more about the nitty-gritty of how these MOFs actually work at a molecular level.
Yeah, let's dive into that. So how do these MOFs actually work? Like, how do they grab onto those gas molecules?
Yeah, that's what I'm curious about. Are they like little traps? Or is there some kind of chemical reaction going on?
It's well, it's a little bit of both, actually.
Oh.
There's a couple of ways it can happen. One is called physisorption.
Physisorption.
Yeah, basically the gas molecules just kind of get stuck to the surface of the MOF pores.
Stuck how? Like with glue?
Not quite. It's more like, remember those weak intermolecular forces we talked about way back when?
Oh, yeah, yeah, like Van der Waals forces and stuff.
Exactly. It's like that. The gas molecules are held in place by those weak interactions.
So they're just kind of clinging on.
Yeah, pretty much. Think of it like a Post-it note sticking to a wall. Not super strong, but enough to hold it there.
Gotcha. And you said there was another way.
Right. Chemisorption. This one's a bit more permanent.
Okay.
An actual chemical bond forms between the gas molecule and the MOF.
Oh, so that's a lot stronger than just clinging on.
Definitely. More like gluing something down instead of that Post-it note.
Makes sense. So sometimes they're clinging, sometimes they're bonded. What decides which way it goes?
Well, it depends on a few things. The type of gas molecule, the specific MOF we're using.
Okay.
Sometimes the MOF is designed so that it'll only bond with certain types of gas molecules.
So it's like super picky.
Exactly. We can make them that way. But speaking of picky, pore size plays a big role too, right?
Yeah, we talked about that earlier. Bigger pores for bigger molecules.
Right. But it's not just about size. The chemistry of the MOF itself matters too.
Okay.
Like what's its surface area, what kinds of functional groups are hanging around, what metal ions are used in the framework.
So it's not just the size of the holes, but what those holes are made of.
You got it. Scientists can tinker with all those things to make an MOF that's perfect for capturing and storing a particular gas.
This is getting pretty complex. How do they even make these things?
The synthesis, well, it can be pretty complicated, but it's gotten a lot easier over the years.
Okay.
Basically, you mix the metal ions and organic linker molecules together under very specific conditions.
And then they just, like, form the MOF.
Yeah, it's a self-assembly process. The molecules kind of know where to go and how to arrange themselves.
Wow, that's amazing. Like a molecular recipe or something?
Yeah, kind of. And
Yeah.
just like with cooking, you got to get the ingredients and the process just right.
Right. So all this MOF stuff sounds pretty awesome. But are there any downsides?
Well, nothing's perfect, right?
True.
One challenge is stability. Some MOFs are sensitive to moisture or other environmental factors.
So they might not last very long.
That can be a problem, yeah. Researchers are working on making tougher MOFs, ones that can handle real-world conditions.
And what about cost? Are these things expensive to make?
Some of them are, yeah. The materials can be pricey, and the synthesis can be complex.
So scaling it up for industrial use could be tricky.
That's one of the hurdles, for sure. But scientists are working on finding cheaper ways to make them.
Makes sense. Well, even with the challenges, this MOF stuff is super exciting. It's like science fiction coming to life.
Yeah, it really is. It's amazing what we can do when we understand how chemistry works, right?
Absolutely. We're
yeah.
using chemistry to design materials that could change the world.
It's inspiring, isn't it?
Totally. And you know what? This whole conversation has got me thinking. So we've been talking about MOFs capturing CO2 and storing hydrogen and even delivering drugs. But if scientists can design them to capture specific gas molecules like that, could they design them to capture other things too?
That's a great question. And the answer is yes, potentially. Yeah. I mean, think about it. The whole beauty of MOFs is that they're so tunable. We can tweak their structure, their chemical properties,
Right.
to target all sorts of different molecules, not just gases.
So what other sorts of things could we capture?
Well, the possibilities are pretty much endless. We could design MOFs to capture pollutants from water, for example.
Oh, wow. So like cleaning up contaminated water.
Exactly. Or how about an MOF that captures harmful viruses from the air?
Whoa. That sounds like science fiction.
I know, right? But it's not as far-fetched as it sounds. The key is to understand how the MOF interacts with the target molecule. Once we know that, we can start designing MOFs with very specific functionalities.
So like we're playing molecular matchmaker, finding the perfect MOF for each job.
Exactly. And the best part is this whole approach is super sustainable. No harsh chemicals, no energy-intensive processes,
Yeah.
just good old-fashioned chemistry.
I love it. It's amazing to think about how these tiny little sponges
Yeah,
could hold the solutions to so many of the world's problems.
it is pretty mind-blowing.
Well, this deep dive into MOFs has been an incredible journey. I feel like we've learned so much about these amazing materials, and I'm so excited to see what the future holds for MOF technology.
Me too. It's a field with so much potential. Who knows what incredible discoveries are just around the corner?
Right. And for all our listeners out there, keep those brains buzzing.
Keep exploring, keep asking questions. You never know what you might find.
Well said. And on that note, I think we'll wrap up this deep dive.
Thanks for joining us.
Thanks for listening, everyone. And until next time, Stay curious.